So how do I test for this concavity, this change in concavity? I'm going to use the second derivative. So I'm going to take my second derivative, and if it turns out to be positive, remember this is the notation for that, then I'll actually know that my function is concave up. That's a simple test. And if my second derivative is negative, then I'll know, guess what I'll know? Oh, you guessed it, it's concave down. Now, what you need to keep in mind, though, is that these points of inflection, they're going to happen whenever my second derivative is 0 or it's undefined. Just like when I was solving first derivative, I said equal to 0 and I said equal to undefined. But you do have to make one note about this. There's a catch. There's always a catch, Torres. And that catch is that those possible points of inflection have to be tested, because there is a possibility that they end up not being points of inflection after I get them. So after I've gotten these answers from setting it equal to 0 and setting it equal to undefined, I need to test them to make sure the concavity actually changes. So let's look at an example. The first thing I want you to do is take first derivative of this, pause the video, do it by yourself. Did you get it? Did you get it? Something that I want to go back and do, and I should have done first, but the order doesn't matter as long as I do it, is what's the domain on this graph? I noticed that it may have problems, like I can't have a negative in the square root, so I know that inside the square root must be positive. Could actually equal 0 since I know the square root of 0 is 0. And so I get x squared greater than or equal to -1, which means I have no solution, because a squared number is never, or excuse me, I get all real numbers, because any number that I square is going to be greater than -1. That's the notation for all reals. Okay, so that means my domain, if I put it in interval notation, is -infinity to +infinity. Okay, good to know. I'll need that for later. So now I wanted to test concavity, and I just finished writing that for concavity, I want to look at second derivative. So pause the video, see if you can take second derivative. Did you get it? Did you get it? Here's my second derivative. So now that I have it, now that you have it, I want to see when it equals 0 and when it's undefined. So if I try to set it equal to 0, remember anytime I have a fraction, really that's like setting the top equal to 0, because the only way a fraction will equal 0 is if the top is 0. So I end up with the numerator equaling 0. Well, that's not true. 1 doesn't equal 0, right? There's my numerator. So that's a no solution. So that fraction is never going to be 0. And then I check to see when is it undefined. Well, it'll be undefined, of course, if the bottom is 0. But let's think about this for a second. So when would that bottom ever be 0? Well, even without going through the whole process of raising to the 2/3 and subtracting 1, any number that I put in for x, the minute I square it, what's going to happen? Right, it's going to be positive. And then if I add 1, it'll still be positive. And if I take the square root, it'll still be positive. So that will never be 0. So I'll get no real solution for that. So now I had no solution for when it was 0, no solution for when it was undefined. So this has no possible points of inflection because there's no change in concavity. And I would encourage you to look at this graph, the original graph, on Desmos, just to convince yourself.